Thanks for the invitation and thanks for coming. So I'll talk about today's some recent results in sort of a broader program where most of the things still remain open. So I'll indicate some of the results, but also emphasize some important future directions, and hopefully that's going to generate some interest among the audience here. Okay, so and then I obviously see some experts, but there's also some people who are maybe slightly less familiar with some of the topics here. So I'll go slow, and if we don't cover everything, that's fine. But please feel free to stop and ask questions or make comments. Okay, so and then we'll come back to this figure eventually. But all right. Okay, so a fundamental problem is to understand interface growth or models of growth driven by some underlying disorder. And here are two sort of instances. This is some interface which sort of dictates the front of a forest fire. This is some bacterial colony. And the main upshot is that often, even though microscopically some of these models look very different from each other, at a coarser scale or a macroscopic scale, the fluctuations are supposed to be universal. So some of the microscopic discrepancies are expected to not really be key in driving these universal mechanisms. And this leads to sort of classifying models according to different universality classes. And okay, so a particular example of interest for us would be the notion of a random metric space. And this you can also view as a model of a random growth, because you can just look at the metric balls. And then this sort of as the radius grows, you have a growing cluster. And the most simple to state model would be the model of force passage percolation, let's say on the usual Euclidean planar lattice. So you have vortices or edges on the lattice which now will be equipped with random weights. So let's pretend that every edge is equipped with an IID exponential weight. So this distorts the usual L1 metric on Z2, right? So every edge in the usual L1 distance has length 1, but now it has this random length. So this distorts the metric structure. And then you consider the graph metric to this randomly weighted graph. And this was introduced in the 60s by Hammersley and Welch as a model of fluid flow through random media. And then subsequently, somewhat recently, there was this nice survey which at least reviewed some of the important developments in this topic. But most of the questions still remain open. Okay, so as I said, so if you look at this metric ball in this random metric space and you zoom out, you're going to eventually see some deterministic shape emerging. And this is going to be convex because of some soft subadditivity considerations. And it turns out that this limit shape is not universal. It's going to be a function of the underlying distribution. But now if you zoom in on near the boundary, this is going to be some random interface. And it's expected that the fluctuation theory of this random interface, if you zoom in on the right scale, is not going to be a function of what the distribution of the underlying disorder was. Okay, so the local fluctuation is predicted to be universal regardless of what you start with, as long as it's nice enough. Okay, so and then a related model, which is what the talk will mostly focus on, is last passage percolation. So again, this is again a lattice model. And the key difference is that instead of looking at shortest path, I'm looking at directed longest path. So I look at 0, 0 to NN. The paths only go north or east in this picture. And then I just sum up all the random weights along this path. That's going to be some energy associated to path. And then I look at the geodesic, which is the path which maximizes the length. All right. So some abuse of notation of this word geodesic, but okay. All right. And okay, so now you can look at this, whatever the metric ball in this sort of directed setting is, like you can look at the set of all points which are at distance, let's say some k from the origin, and then you can vary your k. So as the color changes, these are the levels curves. So points on the boundary of this colored cluster are at the same distance from the origin, okay? And now you can these are three different instances where the underlying distribution has some varying features. The first one you can pretend is like, let's say, IID exponentials or something. So it has light tail weights. The second one is IID, but has more power law or heavy tail type behavior. Okay, and this leads to some kinks, because if let's pretend that we are looking at the cluster of all points which are at distance less than 1. Now pretend that this vortex at this kink has very large value. because of the heavy tail behavior, which means as soon as you include this point in the cluster, the distance abruptly changes to 100 or something. Okay, so this leads to this kinky behavior in this heavy tail setting, and this is still light tail but has more long range correlations, so again has some sort of more roughness. Okay. All right, so and then again to put it in context, so LPP, we looked at this maximizing energy path, right? So you can think of this as a zero temperature version of a more softer model where you put a probability measure on paths, where the probability of a path is proportional to, let's say, something like the exponential of beta times the length. So obviously, if beta were infinity, which is beta is this inverse temperature parameter, so if beta were infinity or close to infinity, the entire mass would degenerate to the largest path, which is what the LPP model is. And so as beta goes from 0 to infinity, so if beta were 0, this would just be a uniformly chosen path, right? So there is no effect of the disorder. So as beta sort of moves from 0 to infinity, you have this interpolating family of measures which goes from random walk-like behavior to a very degenerate measure which sort of completely sort of focuses on this maximizing path, right? So is the model clear? All right. And so, as I said, like, so the fluctuation theory in this model is expected to depend on things like the correlation structure of the underlying disorder variables and their tail behavior and not much else. Okay, so, and so sort of the theme of this talk is going to be sort of trying to initiate a study of models like this in certain critical environments. I'll make precise what I mean by these, but before that, even let's sort of review what is the situation with the simplest setting where things are all IID and have very nice tails. Let's exponential. The exponential case is a bit special, but let's say exponential tails is already sort of something that most of the results are not known, even though there are some strong predictions. Yeah. So this particular setting where things are IID and light tailed is supposed to be sort of governed by this what is known as this KPC or Kardar Parisi Zhang universality class. And so again, I will not spend too much time, but just to sort of give a snapshot. So this basically says that this growth model is supposed to be in line with the behavior of a canonical nonlinear stochastic PDE. Okay, yeah, because of time constraints, let's not sort of dwell too much on this, but just sort of the mechanism is like this is the height function of the interface, and so t is the time coordinate as you sort of evolve in time, and x is the spatial coordinate, and so. So the key feature is that there is some random forcing term or the white noise here, and then there are some nonlinear terms which is sort of characteristic of this model. Okay. So what is expected and what is known? So you are going from 0, 0 to nn. So it's expected, and this is actually not very hard to prove, and this is sort of known very generally, that the leading order behavior of the energy of this maximizing path is going to be some constant times n. Right? So like there are n many vertices on this path, and you're trying to maximize, and everything is light tail, so nothing is huge. So overall, you will make constant progress. So you get c times n as your leading order behavior, and the more interesting thing is like to understand what are the second order corrections. So ln, which is this length of the geodesic, minus cn, which is this leading order behavior, is expected to be fluctuating as n to the some exponent chi. Okay. And the other sort of natural observable is like you look at the path itself. So if the path were truly random, if it was a random walk path, you know that it would fluctuate by square root n in time n from the straight line. But this is not a completely uniformly random path. This is the path that maximizes the length. And it turns out that there is this other exponent psi which is supposed to govern this fluctuation of this path. So by TF, I mean transversal fluctuation, which means how much the path deviates in the orthogonal direction from the straight line joining the endpoints. And so there is this two characteristic exponents chi and psi. And it's expected, this is what is known as KPZ scaling relation, that chi and psi are related by this linear relation. So chi is 2 psi minus 1. And this is supposed to be dimension independent. This is supposed to be true in all dimensions, this relation. However, for d equal to 2, it also is expected that chi and psi has a special values of 1/3 and 2/3. So obviously this equation alone is not enough to sort of come up with these numbers, and so there is some further consideration going on, which I'll only hint at but not go too much on this. So yeah, so as I said, the exponents arise from some universal mechanism, and at least in the two-dimensional case, the main sort of feature that gives you this 1/3 and 2/3 is like some parabolic curvature. So you saw that this limit shape was convex, This metric ball looked like a convex body from far away. So this is some parabolic behavior, so some convexity. And then this sort of IID disorder gives you some local Brownian fluctuations. So there is some competition happening between some global sort of parabolic tendency to some more local Brownian type fluctuation. And if you see what kind of exponents sort of arise out of that competition, you will get this 1/3 and 2/3. And, but this is only at the prediction level. So such predictions have so far only been proven in the class of exactly solvable models. Yeah, go ahead.
This should work in any dimension, this curvature argument.
Yeah, but the Brownianity is not true anymore. Yeah, so there is this curvature part is fine, but the Brownianity is a one-dimensional thing. And okay, so obviously Kurt was one of the central players in whatever development there has been in this sort of integrable world where you take some models which has certain extra algebraic properties and you can take advantage of those to prove these predictions. And so in particular, an example for which this is known now is where the IID variables are all IID exponentials or IID geometric variables. But this paper of Baik, Deft, and Kurt started with the model of random permutations, which is also can be cast in this sort of language. Okay, so we'll sort of focus on a class of models where this KPZ theory is not expected to be true. And for reasons that will sort of become apparent soon, so we call this model sort of class of models critical. And so criticality, one of the key features that we will sort of encounter is that so instead of having like just IID disorder, the environment will have some decomposition into a hierarchy of IID disorders, but one per scale. And so a canonical example of such a process is the two-dimensional Gaussian free field, which is luck correlated, which has, at least in some coarse sense, can be thought of as a superposition of white noise disorders, but at different scales. Okay. Okay, but still staying with the IID picture, but now let's sort of shift our perspective to a more heavy tail setting. Let's say the IID distributions have power law tails now. So let's say every random variable has this alpha decaying power law tail. So probability x bigger than t decays like 1/t to the alpha. And so the KPZ exponents, like this 1/3 and 2/3 exponents, are not supposed to be true anymore. But there is some heuristic argument which does predict something in this setting. And so what is the heuristic? Again, there's going to be some algebra involved, which I'll not get into. But so let's pretend that the path deviates by n to the psi, where psi is now a function of alpha. Okay, so alpha is this tail exponent. So recall that psi was supposed to be 2/3 in this KPZ picture. So now it has psi alpha, where there is some alpha dependence. And so the prediction is, so the KPZ relation is supposed to be true, which is chi is 2 psi minus 1. So that linear relation is true. But the 1/3 and 2/3 is replaced by this new consideration where the fluctuation of the energy is driven by the largest weight variable that appears in this strip. Right? So if you have a heavy tail environment, occasionally you will have some very large values that appear. And the heuristic is that those are the ones that dictate fluctuation. So you can do some algebra to see if you have a strip of this width, what is the largest value that you typically see, and then you can equate that to chi. So this gives you another equation, right? So there was this KPZ equation, which was chi is 2 psi minus 1. And there is this other equation which says chi is 1 plus psi over alpha, because this is the exponent of the largest weight that you see in this strip. So now you can equate these two, and these are now two equations and two unknowns. So you do something, you get some rational numbers, rational sort of expressions involving alpha. Okay. Anyhow, so this is all very heuristic at this point. But like now you can plug in alpha equal to 5 in this picture, and you get this KPZ exponents 2/3 and 1/3 back. So the expectation is, okay, so one more comment. So again, if you do some algebra, you can see that psi, which is the exponent of wondering how much the path moves by, the path cannot move by n, right? Move by more than n. So this is an n by n box, everything is directed. So obviously, this number psi is less equal to 1. So that actually says that this prediction can only be true for alpha as long as alpha is bigger than 2. If alpha is smaller than 2, psi becomes bigger than 1, so that does not make sense anymore. And in fact, for alpha less than 2, which means quite heavy-tailed, the picture is actually much simpler, and this is actually more or less fully understood. What turns out to be the case is that there's going to be some order 1 many large variables, and the geodesic is simply going to try to pass through some of them. Okay, so Again, it's not very important. The main upshot is like, so if you vary your alpha from 2 to 5, these are expected to be your exponents. And from 5 onwards, the exponent is supposed to be 2/3 and 1/3 universally. Okay? That's supposed to be the prediction.
I thought that when alpha is 1, you're supposed to have a scaling limit of the path. I mean, this is...
No, for 2, as long as it's smaller than 2. Because you see that the largest weight is n over 2 over alpha.
Right, yeah, no,
and this is, as soon as this is superlinear, you get scaling limit at this scale.
So if you take alpha equals 2, then you have an integral.
Yeah, this is the critical situation that we'll talk a little bit about. Yeah, yeah. Okay, so turn to the critical alpha equal to 2 case. And so as indicated, this admits a multiscale structure, the noise. And again, so you have this n by n box. And so you have, and so you look at, let's say, some dyadic scale k, 2 to the k. And so what will happen is if you take your box of size 0 by n by 0n and you tessellate it 2 to the k by 2 to the k boxes, inside each box, the largest weights are going to be of size typically 2 to the k at this alpha equal to 2. Again, this is some algebra going on. You don't have to pay too much attention, but this is the truth. And so in each box, there's going to be order 1 many such variables of this weight. So basically what this says is that this noise model in the critical case can be thought of as superposition of log n many Poisson point processes, each one for each scale. For the kth Poisson point process, the weights are 2 to the k, and the intensity is like 1 by 2 to the 2k or something. Okay, and this is just like you sort of do some algebra with how the critical noise model looks like. So any questions so far? Okay, so, and it turns out that also from this sort of heuristic picture of the exponents as a function of alpha that I indicated, as Marek pointed out, alpha equal to 2k seems to be the transition point for this k-pizza relation to hold. It's also expected to be the transition point where the passage time goes from being concentrated to not concentrated. So if alpha is smaller than 2, the passage time is not concentrated. If you divide by the leading order behavior, it's a random variable at that scale. Okay, good. So the other sort of, and this sort of hierarchical decomposition naturally brings us to this more classical sort of Gaussian free field-ish object, which is a hierarchical approximation, which is a branching random walk. So here what you do is, instead of having a single point with a large weight, you tessellate your box again with 2 to the k by 2 to the k boxes, but now for each entry inside this box, you have a single Gaussian, right? So again, this is a picture stolen from Marek's paper where you have this is your base space, which is an n by n box. And now for each lattice point, you sort of have this hierarchical tree where you decompose it diagonally at every layer. And every box is equipped with a single Gaussian. And the weight at a particular vertex downstairs is simply the sum of the Gaussian weights along the tree up to the root. Okay? So I guess most people are already familiar with this, and this is again like a hierarchical sort of version of the Gaussian free field, and this is what I just said. So the actual Gaussian process at a given vertex v downstairs is simply the sum of the IID Gaussians along the geodesic up to the root.
So you're actually assuming the perfect scaling structure, not that you divide the distribution and.
Yeah. So this is, yeah, exactly. So so some of these things will be mentioned as open problems at the very end. So this is like the very sort of coarse hierarchical, yeah.
But in principle, you can simply take this distribution with the tail and divide up the support.
Oh, yeah, you can do that too. Yeah. Exactly. Okay, so this brings us to this topic of last passage percolation and the Gaussian free field. So although what I stated in the previous slide was a hierarchical version of this, so there's been obviously a lot of recent progress about Liouville quantum gravity and pre-limiting models. And these are supposed to be like scaling limit of first passage percolation driven by, let's say, exponential of gamma times the Gaussian free field, or some discrete versions thereof. And you can also look at natural directed versions, which is what we are focusing on in this talk. And they should converge to some directed version of the LQG metric. Okay. And okay, so this is a slightly sort of maybe speculative point. So, and okay, so obviously it's true in some sort of regime. So LPP and the GFF you can think of as a very, very high temperature limit of directed LQG. because directed LQG is a directed path driven by this disorder, which is exponential of gamma times the Gaussian free field. Let's pretend that gamma is very, very close to 0. So you can linearize the exponential. So it's 1 plus gamma times the GFF. And each path has n many vortices on it. So the one part has no, so it's a deterministic effect. So you can center it out. And so then it sort of basically boils down to LPP on the GFF environment itself. Okay? But obviously, I mean, like if you look at the continuum model, there are certain sort of subtle issues about in which way do you take limit, whether the Taylor expansion is sort of permitted or not, and things like that. But at least in some sort of regime, this ought to be a good approximation. Okay, so the picture is you have log n many layers of disorder, one per scale, and this hierarchical structure is expected to sort of give you new logarithmic correction terms in how these models sort of behave. So in particular, let's say the energy, which was linearly growing in the usual case, is now expected to grow, let's say, it's not sort of unnatural to speculate that this is n times some polylog term, because there are log n many layers at play. Similarly, you can look at the fluctuation, and so there could be some polylog terms here as well, and so in the sort of transversal fluctuation setting. And it turns out that although there are some speculations in the physics literature about some of these exponents, there is no precise thing because somehow some of their computational powers are limited, and it's sort of very hard to really pin down exactly what exponents of log appear in some of these settings. Okay? So there are very few like precise numerical predictions about this A, B, and C. Okay, so what is the broad hope? The broad hope is, okay, so you have every layer is sort of somewhat in the KPZ universality class because it's just white noise at a given scale. And so maybe we hopefully understand that reasonably well by now. And so now you can try to sort of come up with a program involving some multiscale analysis that allows you to patch up the effects across the different layers. And so KPZ inputs for per scale coupled with some multiscale analysis could give you some hope of pinning down some of these exponents. Okay, so that is the broad sort of hope. Any questions? Okay, so and here is sort of the picture that which sort of represents what I just alluded to. So again, so let's say, so this is the blue microscopic curve is, let's say, the geodesic. And now I can sort of decompose it into different skeletons depending on what scale I look at. And so the red scale is so the red path is the coarsest skeleton, which is looking at basically the coarsest boxes that the geodesic passes through. And then I can refine it further into this yellow path, which is sort of the next scale. And eventually I'll get the finest path, which is the geodesic. But then for every layer, there's some skeleton that I can draw, depending on which boxes the geodesic passes through at that scale. Okay. And so, okay, so let's see. So you have log n many layers, and each layer is like KPZ, and we know KPZ sort of grows linearly. So somehow a trivial upper bound of n log n holds, although that might not be quite far from the truth. So if you look at how the energy of the LPP value grows in this new model, it should be no more than n times log n, right? Because there are log n many layers, each layer is like linearly growing at most. And so even if the paths were completely additive, which is obviously somewhat absurd, that the best path is also the best simultaneously across all layers. Even if that were true, you would not get something more than n log n. Okay, so we'll sort of talk about the upper bound eventually, but let's for the moment focus on lower bounds. So in this heavy-tailed model, in this sort of recent paper with Victor Ginsberg, who's my student, and Kyung-Sik Nam, who was a former Berkeley student now back in Korea, so he proved that with very high probability, the passage time or the energy of the geodesic is bigger than n times some log n to the 3/4. So n log n is a trivial upper bound. N times log n to the 3/4 is a lower bound that you can construct. So this is obviously a constructive proof. And I'll talk more about this. And on the branching random walk side, and so there's obviously some spurious log n terms which should be removable, but this is what the result says. On the branching random walk side, the lower bound that we have is n times square root log n. Now recall that square root log n is the typical value at a given point on the branching random walk, right? A Gaussian on a branching random walk is the sum of log n many Gaussians. So its variance is log n. So its typical value is root log n, but with both a plus or a minus sign equally likely. And this one basically picks up the positive values in some sense. Right? So a typical point would be like plus square root log n or minus square root log n with equal chance, but this is a maximizing path, so this somehow you can show, what this basically says is you can arrange for the path to pass through mostly positive root log n values. Yeah?
Sorry, what is Ln in the branch random walk setting?
Sorry?
What is Ln in branch random walk setting?
So it's the same, right? So it's you give you an environment, you look at the maximizing energy of paths. Is that what your question was?
What is the environment here? Is it just
The branching random walk. So you have a Gaussian process on an n by n box, which was constructed according to this tree. Yeah.
But here I have one. Do you suppose these two lower bound will match in the end?
So I'll comment on that. Okay. And then the next result is about concentration. So what we prove is, okay, so for the moment, let's focus on this alpha equal to 2 critical heavy-tailed case. So Ln, which is the energy minus its expectation, divided by n is tight. So what it's saying is that Ln minus expectation Ln has fluctuations no more than n. And so in particular, we also have some power law tail bounds, but that's not super important. And so expectation of Ln, as we from the previous slide itself, follows that it's bigger than n times some polylog. So this indicates some concentration. So the Martin and Hamler result says for alpha less than 2, you don't have concentration. Things are all random variable at the right scale. And for alpha bigger than 2, the Flory argument predicts that it's concentrated. And this is saying that even at the critical point, it should be concentrated. It is concentrated. Okay. On the branching random walk side, the fluctuation is actually tight. So previously, okay, sorry, just a second. Here I said this is tight, meaning that a priori the fluctuation could be smaller than n. This is how I sort of formulated the result. But on the branching random walk side, actually this is tight. The fluctuation of the passage time is of order theta n with Gaussian tail. Now the fact that it's lower bounded by n is seen trivially from the top layer, right? So if you look at this vortex, the top vortex, that's actually having an effect on each of these vortices downstairs. And so which means the energy of the path is n times that vortex plus other stuff. So if that vortex moves by order 1, the top vortex, the entire energy of the path, of every path moves by n times that value. So this is a Gaussian, so overall the energy changes by n times the standard Gaussian. So that's a lower bound, and it turns out that an upper bound is also true by standard Gaussian concentration inequality of the maximum, by like Borel's inequality or Sorelson or one of these. So in the branching random walk case, really n is the order of the fluctuation, whereas the leading order behavior is n times some polylog, and the lower bound currently is n times square root log. So that's the picture. And regarding the previous slide, for the critical case, we actually expect the fluctuation to be sublinear in n. Although the previous slide proved tail bounds at scale n, we expect it to be n times actually some polylog, n by polylog. So it should be strictly smaller than n. Okay, so how does one prove a lower bound? So to prove a lower bound, you just have to exhibit a path which is high energy, right? That's what the lower bound entails. So you can try to construct a path with a large passage time scale by scale, okay? And so I'll briefly sort of describe what is being done, but as we will see, like this sort of scale by scale construction leads to a natural trade-off which has to be sort of analyzed. So let's just do some cartoons. So let's just take two consecutive Poisson point processes with different intensities. So let's say this is a Poisson process of intensity 1. So I give you this. And then there are obviously log n many more Poisson layers that will come after this, but let's for the moment just look at this. And let's say I prescribe some skeleton of the geodesic, without looking at the next layers. So I just give you this layer, I tell you, I want to just look at sort of paths which have this as the skeleton at this scale. Okay, so I forget all the remaining points because I'm done with this layer. And then I introduce the next layer of Poisson process of intensity, let's say 4, but now with a factor of 1/2 in the weights. But because of the directedness constraint, the Poisson process in this sort of white region does not matter, right? Because if I fix my blue skeleton to be through these points, the only red points that I can associated to the path to keep this as the skeleton at the blue scale are the Poisson points inside these boxes, right? Because of the directedness constraint, any red path here, any red point here, if I force my path to go through this point, it would violate the fact that this blue point was in the blue skeleton. Okay, so now you see some natural, okay, so this is what I then do. So this is some red skeleton that I now specify at this scale, and then I can iterate. Okay. But, okay, so here is the main point. So if I deviate too much from that straight line, I'm going to have less and less points that I have access to because of the directedness constraint. But I also need to deviate a little bit because otherwise I will not find too many points at the current scale, because obviously there's some entropy, and so there are not too many Poisson points near the diagonal, right? So in one sense, you have to deviate a little bit to ensure that you have enough points at this current scale, but deviating too much will make the subsequent scales lossy. So you have to decide exactly how much to deviate at per scale to make this sort of overall strategy somewhat fruitful. And so the proof and the choices involve sort of dealing with this trade-off, which obviously I'll not comment too much on. And as a byproduct of our analysis, we answer a long-standing question of James Martin on the growth rate of LPP and how that's related to the distribution. So I said like the growth rate is linear in n typically, and that's by some subadditive considerations, but that's only when the underlying disorders are somewhat light-tailed. Again, if you have heavy tail, as we saw, things can be sort of quite fast growing. So, and then the rough question was whether a finite second moment of the underlying disorder distributions was enough to ensure finiteness of the growth constant. And that turns out to be not true. And you can use this sort of multiscale analysis. Obviously, the critical point that we were talking about, 1 over t to the alpha, where alpha is 2, that does not have finite second moment. But you can add some logs to make it finite, but still sort of play around with things to actually answer this in the negative. So you can construct a modification of this critical environment which now has finite second moment, but the growth rate still diverges. So any questions? Okay. And so as I said, for branching random walk, we proved that the growth rate is n times square root log n up to this polylog factors, which is sort of should not be there. And again, the construction there sort of proceeds in a similar way, where you again sort of do a multiscale construction and you choose optimal paths per scale. The precise lattice details are sort of somewhat cumbersome to present here, but again, the strategy is not very different. And one thing which sort of why this strategy leads to a root log n instead of a log n to the 3/4 is unlike the Poisson case. In the Poisson case, if you hit a good point, you pick up a large value. Whereas here you have to sort of pass through the box entirely to pick up large values, because there's no single point which is large, but somehow the same variable appears at every point in this box. And also there are negative weights, so that leads to further cancellation. And so which is why you don't get, even though the strategy is somewhat similar superficially, the outcome is somewhat different. And in fact, as I'll sort of try to make a case soon, we expect this to be tight in this case. We expect n root log n to be the tight bound in this GFF setting. Okay, so upper bound. So again, as I said, n log n is an upper bound which is trivial. Here it's even more trivial because the maximum of a branching random walk on an n by n box is log n. Each variable is typically like root log n with a plus minus sign, but the overall global max is like order log n. So obviously a path has n many vertices on it. No vertex is more than log n, so obviously the energy cannot be more than n log n. So that's a trivial argument. But now let's try to see what would allow this to be sharp. I mean, this. So the global max is like, let's say, log n with a particular constant. Let's say, I don't know, 2 or root 2, one of these. But let's look at all the vertices that are of size 0.1 log n. Okay, so it's so something which is comparable to the maximum, which are what are known as thick points. Okay, so suppose you had a directed path which passed only through thick points, only through values that are 0.1 log n or more. then obviously that would give you a lower bound of n log n up to constants immediately, right? So somehow this sharpness of this upper bound is pretty intrinsically, pretty sort of deeply connected to this notion of percolative properties of thick points, or oriented percolating properties in particular. So you look at the set of thick points, meaning the points which have values that are up to constants like the maximum, and then this is going to be some fractal subset of your domain, and now you want to ask whether it sort of admits some directed path through that set. Okay? Right? So does that make sense? So this is the question: does the set of thick points oriented percolate? And so an easier setting could be fractal percolation, which is, okay, so I'll describe what this is. And this is going to be some proxy for the set of thick points. So again, what you do is like you have a branching random walk type situation. And so now let's say for every vertex, you have a Bernoulli P random variable. And let's say eventually this is your eventual domain. And every vertex here is going to be 1 if and only if all its parents are Bernoulli ones. I mean, all the Bernoulli variables of its parents are 1s. So in some sense, this is like an intersection of log n many percolation environments, but obviously 1 per scale. So a particular vertex in the eventual fractal percolation environment survives if and only if all of its parents are surviving. Okay? And so why is this sort of a proxy for, somewhat loose proxy for the thick points? Okay, so recall, so you have a branching random walks, you have log n many layers. Each vertex is a sum of log n many Gaussians. And I want the eventual value to be bigger than 0.1 log n, right? So it's like a random walk of size log n. And I want the eventual random walk to be at location like 0.1 log n. So which means that more or less the random walk should have a positive drift throughout its journey. So which means all of its all of its increments, these are the Gaussian variables, should have like some positive mean. Right? And so now you can compute the, so this is some, so you want all of these variables to be uniformly, let's say, bigger than 0.1 or something. I mean, this is the part which is not correct completely, but let's pretend that this is sort of the heuristic that we're running with. So every random variable has some probability of being bigger than 0.1. Let's call that, let's say, some p. And so then a particular point at the very end is a thick point if and only if all of its parents were 1 in this sort of Bernoulli P model. Okay? So obviously, this is not the only mechanism by which something can be eventually big, right? So you have a sum of log n many Gaussian variables. Not all of them uniformly have to be big for the eventual sum to be big. So this is where the sort of connection sort of breaks down, but at least this is like a good starting heuristic. And yeah, so if you want the eventual vertex to be bigger than alpha log n, then the corresponding fractal percolation P should be like probability that this Gaussian is bigger than alpha, roughly.
That's just a lower bound, essentially, right? So that gives you...
Yeah. The thick point set is more complicated and bigger, yeah.
But isn't the deciding property the Hausdorff dimension of these?
Yeah. But like somehow, yeah, exactly. So, right. So somehow the main question is like, suppose I give you this set of this Hausdorff dimension dictated by the thickness, whether it admits this percolation property or not is the question. But okay, so but like in the analysis, it's sort of sometimes easier to have more independence, which is what this model provides. Yeah, so now the question is, this connectivity properties of fractal percolation has been widely studied in the literature. So for example, if I did not talk about oriented percolation, but just standard percolation of whether there is a left to right crossing inside this fractal set, and so it turns out that there is a phase transition. So for P smaller than PC, you don't have a crossing, whereas for P bigger than PC, you do have a crossing. And this was this paper by Chase, and Durrett from the 80s. And then if you go to the GFF, then it's sort of the planar GFF, it's known that the set of thick points are totally disconnected in this recent paper by Arrow, Papon and Powell. However, if you're in high dimension, then you actually do percolate. And this is this recent paper by Jian, Yuan, and Zhang. But these are all sort of non-oriented. These are just usual percolation. But the more pertinent result for us, at least in this set of talk, is this result by Lincoln Chase, that if you are looking at oriented percolation in, let's say, d equal to 2, there is no percolation at any p. So you take any fractal percolation with any density p, there's never going to be oriented percolation. Like the set of points that survive in the fractal percolation will not admit an oriented path. Okay, so this is sort of obviously a non-quantitative statement, and somehow if you want to use this kind of an input to upper bound your passage time, you want to do some multiscale analysis. So again, in a forthcoming work with Victor and Kai-Hao, both students at Berkeley, we show that for any P, if you look at LPP on this fractal percolation environment, then it's no more than n times e power minus c log n up to this log n correction. So, okay, forgetting this, and this shows that the LPP value in a fractal percolation environment is polynomially smaller than linear. So which means its value, if you add in the thickness, should be this times log n. Like if this was truly the thick points. So which means that the LPP value coming from large thickness is sublinear in n. And so which means you can go down and then you can sort of maybe speculate that the root log n layer is the only one that contributes where you get n root log n from. So somehow this is still very far away from the claim that I just made because this is still in the fractal percolation world and you want to sort of eventually do it for the actual thick points. And okay, so what is the main sort of point that sort of forces directed paths to not percolate? So the main point is like Chase also proved that any path that does percolate inside this fractal percolation environment, or even the construction of Yuan and Jian and Zhang, so the fractal dimension of a path which stays completely in the thick points has to be bigger than 1. Right? Because this is such a fractal set. If a path has to stay completely inside that set, it cannot be very Lipschitz-like. But the path being directed somehow forces it to be Lipschitz, at least in the discrete setting. Like if it goes n units in this way, in the other way it cannot go more than n. So this sort of Lipschitz constraint forces it to not be able to sort of stay completely in this sort of fractal set. And so in this vein, there is also a geometric result which says that if you take fractal percolation and you take any Lipschitz curve, and if you look at the intersection of this curve with this fractal set, its one Hausdorff measure is 0. So somehow this is again evidence that Lipschitz curves cannot stay completely within this fractal set. Okay? Yeah, as I said, like this is still at the level of the fractal percolation, so the next step is to work with thick points. Okay, and then the sort of the other sort of direction which is related, which I also wanted to briefly touch upon, are positive temperature models. So instead of looking at this LPP, which is the maximizing energy path, often working with softer models gives you more handle on things. And as I said, like there's this parameter beta. As beta goes from 0 to infinity, you go from more random walk-like behavior to like this degenerate behavior. And somehow if you can sort of understand some intermediate values of beta well, and then you can treat beta as a parameter and you can try to understand how things change as beta varies, that's also often a useful sort of way to understand some of these models. And this is just a reminder again, LPP is this zero temperature version of this directed polymer model where the probability of a path is proportional to exponential of beta times the energy. And for IID light tailwinds where things are KPZ, it turns out that if you take your beta to be suitably scaled as a function of the system size, and again the precise exponent is not very important, like if beta were to go to 0 as like n to the minus 1/4, you can take some continuum limit of this path measures. And this is known as this continuum directed random polymer. And this is the partition function of this is a solution to the stochastic heat equation with multiplicative white noise for people who are familiar with these terms. And so formally this is, and this solves this natural stochastic PDE. And formally this is this partition function. So it's the exponential of expectation under the Brownian measure. So you see like, so when I said like, so you interpolate from random walk-like behavior to LPP. So if you do things scaled properly, then your base measure is going to be some Brownian and you're going to tilt it with respect to exponential of integral of this energy term. And this energy is going to be white noise evaluated on the Brownian path. Again, it's not very important. The point being that this zero temperature model can be softened a little bit to take some positive temperature scaling limits. And often studying that is a useful way to get zero temperature behavior or at least evidence of zero temperature behavior. And so in ongoing work with Victor, we construct and analyze this continuum detector random polymer, but in this log correlated environment where the underlying disorder is not white noise anymore, but rather the Gaussian free field. And the construction of the polymer measure proceeds via thinking of it as a Gaussian multiplicative chaos, but now on path space. So we encountered this term GMC in one of the earlier talks, and now you can think of these models as GMC, but when the base measure is like Brownian measure in some sense. Okay, so the Liouville quantum gravity measure is the base measure is Lebesgue measure, and you take the exponential of the Gaussian free field, but you take a suitable renormalized limit, and you sort of do a similar story, but on path space to make sense of these objects. And but like the key point here being that the disorder now has multiple scales of noise, and now you have a temperature parameter 1 per scale. So now you actually have an infinite sequence of temperature parameters. And this gives a framework to sort of tune them to send them to infinity in various rates to probe different aspects of zero temperature behavior. And so here is a very sort of informal way of saying what the theorem says. So let's say P is the Wiener measure, and let's say HN is the Gaussian free field, but only restricted to the top n layers. So this is still a smooth Gaussian process. And now you take some path measure, which is whose density with respect to the Wiener measure is exponential of this Gaussian free field integral along this path, but not the Gaussian free field, but only the first n layers. So this is still a smooth process, and then you renormalize appropriately to make this mean 1 or something. And it turns out that almost surely in the realization of the Gaussian free field, this sequence of measures weakly converge to a limiting measure, and this is going to be this positive temperature scaling limit of this GFF polymers. And as I said, so one of the key sort of advantages of working with a model like this, which is softer than the zero temperature one, is it inherits some properties of Brownian motion. So these are still like Holder 1/2 type paths, but it's also on the other hand singular with respect to Brownian motion. So it's some mix of some aspects of both the Wiener measure and the zero temperature measure. And so somehow this allows you some flexibility to study different aspects. And the proof of this convergence, sorry, model's out of time, right? So yeah. So let me just wrap up. Yeah. And the proof relies on some very careful analysis of intersection local time of Wiener measure in one dimension here. Okay, just quickly wrapping up. So yeah, so go ahead.
Is this like a small temperature, high temperature result?
Yeah, this is intermediate disorder. So you have to really sort of
you do like a second moment.
Second moment and other martingale arguments. Yeah. This is like exactly the analog of CDRP. So CDRP is an intermediate disorder. So you take beta to be going to 0 as the system size goes to infinity. So here you do something analogous, but you have to be careful about what the correct scaling of temperature per layer is. But yeah. So some broad directions. So obtain sharp exponents. So we only presented some bounds. The other thing is like this is also of a lot of interest in LQG itself. Like if we look at the geodesic, you look at the weight profile of the paths along the geodesic, like how thick a typical point is on the geodesic. You can ask similar questions here as well. And so direct Liouville quantum gravity metric is sort of something that is obviously an important thing to construct, and there are people in the audience working on similar sort of themes. And so here is a speculative set of directions. So, and this is more or less maybe for experts. So for people who are familiar with this direct landscape, that's sort of a scaling limit of models in the KP's universality class. And somehow you can think of that as sort of connected to sort of edge eigenvalues of a random matrix, which has trace-evident fluctuations. Now you can think of some bulk version of this story, and the bulk eigenvalues have Gaussian free field-like fluctuations. So you can sort of speculate maybe that LPP on sort of a GFF-like object might have something to do with a putative-like version of the landscape, but now driven by bulk eigenvalues, not edge eigenvalues. And this is completely sort of speculative at this point, but it could be an interesting direction. Yeah, so this is what I just said, and I'll stop here.